Hello everybody. So in this video we're going to talk about Cholesky decomposition and mind you that this is the third time I'm trying to record this video. I realized the previous two times that my mic wasn't on and I tried to fix it and then it just kept some problem or the other kept recording. Anyways, in this video we're going to basically have a brief introduction into how to go about doing a Cholesky decomposition on any given matrix. And after following the purpose of this video, which is to have a brief introduction, we will have several videos following this that shows how to go about applying this in finance, particularly in a geometric Brownian motion modeling for, say, some fx pair. And we will see how we can go about making uncorrelated matrix into a correlated matrix using Cholesky decomposition. And we will first see its algebra, and then we'll go about executing it in Python. So that is the objective that I'm trying to satisfy with the series. So let's get cracking. So what is a Cholesky decomposition? Cholesky decomposition is basically a very powerful numerical optimization technique which involves decomposing a given matrix into a product of a lower triangular matrix L and an upper triangular matrix U. So if I have, say, given a matrix A, I want to decompose this into L transpose. This is very much similar to what we deal with in the when we deal with algebraic equations. When we try to factorize something, we factorize by taking out its factors and then we go about factorizing it. Similarly, in linear algebra, although the factorization process isn't that simple and there are multiple ways to go about decomposing or factorizing a matrix, Cholesky decomposition is by far one of the most efficient and powerful factorization methods out there. So this equation that I've written right here, so this A is the matrix for which you're given a set of values in the matrix, and L basically stands for a lower triangular matrix. And when we multiply the lower triangular matrix with its transpose, we should be ultimately getting the original matrix that we started off with. And this has various applications that can be that is there. One of which being solving a general system of equations, and another one being what I mentioned earlier about being able to make a correlated matrix out of an uncorrelated matrix. So when can we apply a Cholesky decomposition? A Cholesky decomposition is contingent on two conditions, which is that the matrix that is given A should be a Hermitian matrix, and two, it should be a positive semi-definite. It is also quoted in many literature that your the rule is basically that your matrix should be symmetric and should also be a positive semi-definite. We will see now, I will show now why symmetric matrices are nothing but a special case of Hermitian matrices, and we will see how these two definitions are basically one and the same. So what is a symmetric matrix? A symmetric matrix is any matrix when transposed will give the original matrix. So in a sense, if you are given A and if I take the transpose of it, it will be equal to each other. So one good very example of symmetric matrix would be, say, 1 2 3 2 3 4 4 and 5 6. So if I take a transpose of this matrix, by transpose I mean if I were to convert these rows into columns into another matrix, reorient the rows into columns into another matrix, I will get, say, so if I take this row, it will be 1 2 3. I'll take the second row and put it as the second column. It will be 2 5 4. Third row, and it will be the third column, and it will be 3 4 6. And when we look at it, we see that even after transposing the matrix, the original matrix is maintained after transposition as well. So since we see that A is equal to its transpose, we can confirm that A is indeed a symmetric matrix. Now how is this a special case of a Hermitian matrix? Well, we need to first understand what a Hermitian matrix is to understand how is it how is a symmetric matrix a special case of Hermitian matrices. So a Hermitian matrix are basically complex valued matrices. So essentially, these are matrices with imaginary, which also deals with the imaginary realm other than the Cartesian realm, right, or the real valued realm. So so if I were to show you an example, if I define, say, some other matrix like 5, 3 plus 7i, 3 minus 7i, 2. This is a Hermitian matrix because one, it has it is a complex valued matrix because of the presence of these imaginary components, and also it's a Hermitian matrix because along the diagonal you no longer have the exact same like a mirror image of the values of the diagonal. Rather, it's like it has the same magnitude, but the signs on the imaginary part is opposite. So here we have a plus 7i, and here there is a minus 7i. And this is what characterizes a Hermitian matrix, because the symmetric entries with respect to the diagonals are complex conjugates. Complex conjugates means basically they have the same real part, but the imaginary part is opposites in sign, although they have the same magnitude. And this is what a Hermitian matrix is. So now we can clearly see, if the imaginary part were to not exist, and if it is, say, if it is not there, and the matrix is defined solely by the real part, say 5, 3, 3, and 2, then we'll see that this is also a symmetric matrix, right? Because now if you transpose it, B transpose will be the same as earlier, 5, 3, 3, 2, right? So essentially, symmetric matrices are a special case of Hermitian matrices, and Cholesky decomposition can be applied on all matrices that are Hermitian in nature, right? Now, the second condition that was required to be satisfied is that the matrix is a positive semi-definite. So a positive semi-definite can be proved using various tests, but for the purposes of this video, I'm just going to mention one, which is that you'll have to check whether all the eigenvalues of the matrix are of the given matrix is non-negative, right? So this is what characterizes a semi-definite. If it had been just like a positive definite, we would want it to be all the eigenvalues to be positive, and this has the understanding, the intuition behind definiteness calls for another video altogether, because it's a very broad and broad concept, but it is quite intuitive. So there will be many more videos regarding this in linear algebra. So once we establish that the matrix is both a Hermitian matrix as well as a positive semi-definite, we can go about doing a Cholesky decomposition. So to do a Cholesky decomposition, we have a certain amount of formulas that is usually given to students, expecting them to be just memorized and apply them for Cholesky decomposition. And in often cases, we don't even have to do these decompositions ourselves, because the codes that we run can do it for us, right? There are modules in which you can access a Cholesky decomposition function, and then you can apply that. So, but regardless, let's see how we can derive the formulas themselves. And let's do this. So given a matrix A, which is defined by A11, A12, A21, and A22, its lower triangular matrix, let's say, is defined by B11, 0, B21, and B22. Right. This is a lower triangular matrix because the value symmetric to, say, B21 is 0. Right. So on this side of the mirror side of whatever is there on the lower triangular matrix is all 0. So that's why it's called a lower triangular matrix. And we know by the initial characterization that A will be equal to the lower triangular matrix times its transpose. So similarly, if I were to just simply multiply it out, 0, B2, 1, B22, product of B11, B21, 0, B22, this should be equal to A11, A21, A12, A21 and A22, right? And now if I were to just multiply and find the product of these two matrices, it should be B11 squared. So this is this into this, so B11 squared. Now this into this will be B11 into B21, right? Now we multiply this with this column. This becomes B21 into B11. We multiply the same row with the next column, which will give us B21 squared plus B22 squared. And this should be essentially equal to our original given matrix A11, A12, A21, A22, right? So now all we have to do is equate the corresponding entries and see how we can go about figuring out the values of the lower triangular matrix that is part of the Cholesky decomposition. So now we'll just say, for example, this entry B11 squared should be equal to A11, which implies that B11 is equal to root of A11. Similarly, we can take this entry and we can write it as B21 into B11 is equal to A21. Given that we have the value of B11, we can just solve for B21, which is equal to A21 divided by B11, right? So this is our first entry, this is our second entry. Now we can solve for the third bit, which is B21 squared plus B22 squared is equal to A22. Given that we already solved for B21 and we know the value of A22 from the original matrix, this implies that B22 is equal to root of A22 minus B21 squared, right? So when we deal with bigger matrices of greater shape, we will see that there is a general pattern that is recurring with the formulas that we'll have to use when solving for the lower triangular matrix. And in general, we can generalize the above results for elements on the else diagonal. So on the else diagonal, as in the lower triangular matrix is diagonal, as so Bjj will be equal to square root of Ajj minus summation from k is equal to 1 to j minus 1 Bjk squared. And this is for elements on else diagonal. And now for elements of the diagonal, we can generalize it to be Bij is equal to 1 by Bjj into Aij minus summation k is equal to 1 to j minus 1 Bik into Bjk. And this is for elements of the else diagonal for I greater than j, right? So now what I'll be doing is I'll be using these two formulas to do a Cholesky decomposition on a given matrix, on a 3 by 3 matrix. Okay, so let's see if this works, and yeah, let's do this. So this is example. So given a matrix A, which is equal to 25, 15, 5, 15, 13, 11, 5, 11, 21. Let's do a Cholesky decomposition on this matrix, right? So our lower triangular matrix should look something like this now. So So it'll have how many? B11, B21, B22, B31, B32, and B33 as the elements of the lower triangular matrix. Now all I have to do is utilize this formula that was used here. So I'll just rewrite this on the side so that it's easier for me to calculate. So Bjj is equal to Ajj minus summation k is equal to 1 to j minus 1 of bjk squared. And for elements of the diagonal, we can write it as 1 divided by bjj aij minus summation k is equal to 1 j minus 1 bik into bjk, and this is for I greater than j. Okay, now we have the first value that we have to find is for b11, and we know that b11 will be equal to summation square root of a11 and minus 0, because it says that the summation is still j minus 1. So in this instance, since j minus 1 0 does not exist, this becomes non-existent. So this is essentially square root of a11 is equal to square root of what is our value? 25. So square root of 25, which is equal to 5, right? Now b21 will be equal to 1 by b11, for which we know the value from the previous exercise, and into a21 minus again 0, because again this is still j minus 1, and in this instance j is equal to 1, so the summation is still 0, but since it's non-existent, it's not there, so it will become a21 divided by b11. We know the value of b11, and a21 is given in the formula in the matrix given, which is 15. So now it becomes 15 divided by 5, which is equal to 3, right? So far we have b11 is equal to 5, b21 is equal to 3. Now let's solve for b22. So that means we would have to make use of this formula. So this will be basically square root of a22. Now since j minus 1 exists, so j minus 1 would be 2 minus 1 1, so that would mean we will have to take square of b21 whole square squared. So since we know the value of a22 from the matrix and b21 from the previous calculation, we can just compute that. So a22 is 13. So we will be left with square root of 13 minus 3 squared, which is 13, minus 9, which is 4. Square root of 4 is 2, and therefore b22 is equal to 2. Now let's solve for b31. This is the instance where I is greater than j, so we'll have to use this formula. So let's go about doing this. So j is 1, so it will be b1 divided by b11 into a31 minus 0, because j is 1. So now you will have a31 divided by b11. So a31 is given as 5, and b11 we found to be 5. So this would mean that b31 is equal to 1. Now b32 is again the instance where your I is greater than j. We use the same formula, but this time it becomes 1 divided by b22 into a32 minus since 2 is would mean j minus 1 is equal to 1, we will have b31 into b21. We have the value for b31 and b21 from before. A32 is something that we need to take from here. A32 is 11, right? 3, 2. And so upon computation, we will have B22, 1 divided by B22 will be 2, A32 will be 11, minus B31 is 1 into B21, which is 3. So 11 minus 3 is 8, 8 by 2, which is equal to 4. So B32 is equal to 4. And lastly, we'll have to solve for B33, which involves using the L's diagonal formula. So which would compute to A33 minus, so this is a summation from k is equal to 1 to 3, so 2. So yeah, so that would mean we'll have to add B31 squared plus B32 squared, right? And we know the values of everything except for A33, which is in the matrix, which is 21. So upon computation, we will get 20, no wait, was it 21 or 22? 21. Yeah, so 21 minus B31, which was 1 squared is 1, plus 32, B32 squared is 4, which is 16, right? 4 squared is 16. So that would mean square root of 21 minus 17, which is square root of 4, which is equal to 2. Now that we have found all the values of L, we can quite simply just substitute the values into this lower triangular matrix. So we know that B11 is 5, so L is equal to 5. We know that B21 is 3. We know that B22 is 2. We know that B31 is 1. We know that B32 is 4. And we know that finally B33 is 2. And so we have done a Cholesky decomposition on the given matrix A. I hope you have understood everything that I have explained and you have followed everything that I have done. If you have feedback for my style and would like me to improve, please let me know in the comments. And if there are more topics that you would like me to cover gradually over time, that can be written in the comments too. Thank you. Hope you liked my video and will watch more of my videos as they come out. Thank you. Have a good day.